Have you ever wondered what causes the beautiful northern lights or been curious about the recent exceptional sky activity? Well, you're not alone. For centuries, humans have been captivated by these mesmerizing light shows, painting the sky in hues of green, purple, and red. They're not just a feast for the eyes, but also a testament to the fascinating and often complex interactions taking place between the sun and our planet. In recent times, there has been a surge in activity, with these stunning displays reaching further south than usual, gracing the skies of places like Colorado, England, and New South Wales. This unexpected light show can be attributed to a celestial phenomenon known as a geomagnetic storm. But what's behind these skyward spectacles? What forces conspire to create these breathtaking displays? The answer lies in the intricate dance between the sun's activity and Earth's magnetic field. So, what exactly are these geomagnetic storms? Let's peel back the layers of this celestial mystery. Geomagnetic storms are temporary disturbances in Earth's magnetosphere, caused by solar wind shock waves. These storms are a fascinating display of the sun's influence on our planet. And to truly comprehend them, we need to delve into some space science basics. Let's start with the magnetosphere. Imagine a giant bubble surrounding our planet, protecting us from the harsh solar wind that constantly blows from the sun. This protective bubble is the Earth's magnetosphere, created by our planet's magnetic field. It's a crucial shield, deflecting most of the solar wind, whose charged particles could otherwise strip away the ozone layer that protects us from harmful UV radiation. Now let's talk about solar wind shock waves. These are blasts of charged particles or plasma that emanate from the sun. Typically, the magnetosphere can handle these gusts of solar wind. However, during a solar coronal mass ejection, or a high-speed stream of solar wind from a coronal hole, the solar wind shock waves intensify. The coronal mass ejection is like a solar hurricane, ejecting billions of tons of plasma into space at high speed. When these heightened solar winds reach Earth, they can compress the day side of the magnetosphere and cause the night side to stretch into a long tail. When the pressure in this tail becomes too great, it releases, sending a flood of charged particles back towards Earth. These particles stream along Earth's magnetic field lines towards the poles, causing beautiful auroras, but also creating the potential for what we call a geomagnetic storm. Though they might seem like random cosmic events, these storms are not. They follow the sunspot cycle, peaking during what's known as the solar maximum. The cycle lasts about 11 years, and during the solar maximum, the sun has the most sunspots and consequently more solar flares and coronal mass ejections. So, in essence, geomagnetic storms are a testament to the sun's ever-changing nature and its profound effects on our planet. These storms are not random, they follow the sunspot cycle, peaking during solar maximum. The sun, in its ceaseless cosmic dance, creates both beauty and turbulence in our earthly experience. Every geomagnetic storm goes through 3 phases: the initial, main, and recovery. Just like a dramatic play, each act of a geomagnetic storm has its unique characteristics and effects. In the initial phase, we see a sudden shock wave caused by a solar wind, which is a stream of charged particles released from the sun. This shock wave leads to a disturbance in the Earth's magnetosphere, the protective magnetic field surrounding our planet. The magnetosphere starts to compress and store energy, preparing for the main show. The main phase is the most intense part of a geomagnetic storm. The stored energy from the initial phase is released, causing an increase in plasma movement and electric current in the magnetosphere and ionosphere. It's like a massive electrical storm raging high above our heads. The Earth's magnetic field is dramatically disturbed during this phase, which can last from a few hours to a couple of days, depending on the intensity of the storm. Finally, we arrive at the recovery phase. This is when the Earth's magnetic field begins to regain its normal shape and strength. It's like the calm after the storm, as things slowly return to normal. However, the effects of the storm are still felt, especially in our technology, which can be disrupted by the storm's intense energy. To understand the intensity of these storms, scientists use the DST index. This measures changes in the Earth's magnetic field and classifies geomagnetic storms into 3 categories: moderate, intense, and superstorm. The higher the DST value, the more intense the storm. These storms have been observed throughout history, with notable events occurring in 1859, 1972, 1989, 2000, and 2003. From the Carrington event in the mid-19th century, causing widespread damage to the telegraph network, to the Halloween storms at the turn of the millennium, each event has left an indelible mark on our planet and our understanding of the sun's power. The effects of geomagnetic storms are far-reaching, impacting both our planet and human technology. These storms, triggered by solar winds, create a surge of energy that interacts with Earth's magnetic field, causing a variety of space weather phenomena. One such phenomenon is the solar energetic particle event. These events occur when highly charged particles, shot out from the sun, are trapped in Earth's magnetic field. This can increase radiation levels, posing a threat to both astronauts in space and air travelers on polar routes. Then there are geomagnetically induced currents. These are electrical currents that are created in response to changes in the Earth's magnetic field. They can flow through power lines, pipelines, and even the ground itself. While mostly harmless, in extreme cases, they can overload power grids, leading to blackouts. Next, we have ionospheric storms. The ionosphere is a layer of the Earth's atmosphere that's filled with charged particles. During a geomagnetic storm, these particles can become agitated, disrupting radio communications and GPS signals. This can affect everything from your favorite radio station to navigation systems in airplanes and ships. But it's not all doom and gloom. One of the most beautiful effects of geomagnetic storms are auroral displays, also known as the northern and southern lights. These lights are the result of charged particles from the sun colliding with gases in our atmosphere, creating a breathtaking display of colors in the sky. However, it's important to remember that while these storms can cause disruption to our technological systems, efforts are consistently being made to improve our resilience against them and to predict when they might occur, minimizing their potential impact. While these storms can cause some disruption, they also create one of nature's most spectacular shows, the Northern Lights. Recently, geomagnetic storms have made headlines due to their impact on both our skies and our technology. Let's delve into a couple of recent events that have caught the world's attention. In March of this year, photographers and skywatchers were treated to a spectacular display of the aurora borealis and aurora australis, visible further south than usual. This included sightings in places like Colorado, England, and New South Wales. These breathtaking light shows were triggered by solar flares, leading to coronal mass ejections, the very phenomena we've been discussing. As these electrified particles interacted with Earth's atmosphere, they painted the sky with vibrant colors. But it's not just about the beauty. These geomagnetic activities also have practical implications. Take SpaceX, for instance. In February 2022, a geomagnetic storm led to the loss of 40 out of 49 Starlink satellites that had recently been launched into orbit. The storm caused an increase in atmospheric drag by 50%, making it difficult for the satellites to reach their intended orbit. Despite efforts to fly the satellites in safe mode, they were unable to reach their destination and eventually burned up upon re-entering Earth's atmosphere. These instances illustrate the dual nature of geomagnetic storms. On one hand, they gift us with beautiful auroras that light up the night sky, and on the other, they can disrupt our technological efforts in space. As we move closer to the solar maximum expected in July 2025, which is a period of increased sunspots and solar activity, we can anticipate more of these geomagnetic storms. This means more captivating auroras for us to marvel at, but also potential challenges for technology-dependent activities, especially those occurring in space. As we approach the solar maximum in 2025, we can expect to see more of these celestial phenomena. Geomagnetic storms are a powerful reminder of the dynamic nature of our planet and its place in the solar system. These celestial events are born out of the sun's activity, as solar flares and coronal mass ejections send streams of electrified gas and particles hurtling through space. When these particles collide with the Earth's magnetosphere, the result is a geomagnetic storm, a temporary disturbance that can have profound effects on our planet. On one hand, these storms can cause disruptions from increasing atmospheric drag on satellites, potentially making them veer off their intended course to causing notable disturbances in our navigation systems. Yet, on the other hand, they are responsible for one of the most beautiful natural phenomena we can witness: the auroras. These mesmerizing light displays, also known as the northern and southern lights, are a direct result of these solar particles interacting with the Earth's atmosphere, painting the sky with an array of vibrant colors. So, as we've seen, geomagnetic storms are a true testament to the power and beauty of nature, a captivating blend of science and artistry on a cosmic scale. Next time you gaze up at the night sky, remember the intricate cosmic dance that brings about these breathtaking displays.